One more minute. Anybody online? Yeah, Michael is online. Time to get going. So we have two more chapters. Chapter 30 is basic results from quantum mechanics. And chapter 31 is introduction to radioactivity. The main part of chapter 31, we're going to discuss on Wednesday and Friday. And the most important topic is going to be carbon dating. So for the moment, in chapter 30, we talked about Rutherford scattering experiment, which established the existence of nuclei and the planetary model of atom. And well, the results that followed a few years after Rutherford's experiment were about the energy levels of hydrogen atoms and hydrogen-like atoms. And the result was something like this. The ground state energy of an electron in a hydrogen atom is with energy equal to negative 13.6 electron volts. This is the ground state energy. Call it E0, let's say. Oh, yeah, well, not zero. Let's say E1, because this corresponds to principal quantum number equals 1. The second higher energy state corresponding to principal number n equal to 2 has energy equal to negative 13.6 divided by 2 squared divided by 4, and so on. So in quantum mechanics, the spectrum of energy of a hydrogen atom is one of the few examples where the equations can be solved analytically. And the results are that any energy in a hydrogen atom or hydrogen-like atom, the electron is with energy negative 13.6 electron volts divided by integer number n squared. So this formula describes the nth energy level of a hydrogen atom. For hydrogen-like atoms, the formula is similar up to a constant. It's exactly identical. So those are energies of the electron in an atom of hydrogen. Now, the question is, how do you describe the state of the electron in a more complex atom that may contain multiple electrons? And the answer again is given with quantum mechanics. And the answer is that you need 4 numbers to fully describe the state of an electron in any atom. And those four numbers are the principal quantum number n, and that number is integer 1, 2, 3, or so on. In addition to, so the principal quantum number gives you almost exactly the energy of an electron in an atom. For the case of hydrogen, it gives you exactly the energy levels, or pretty much almost exactly. The second quantum number that you need to describe the state of an electron in any atom is called orbital quantum number L. And the value of the orbital quantum number ranges from 0 to n minus 1. So this means that if an electron is in a state with principal quantum number 3, the value of the orbital quantum number for that electron could be any number between 0 or 1 or 2. Those are the allowed numbers for this particular electron. The orbital quantum number gives the orbital angular momentum of the electron in an atom. And quantum mechanics demonstrates that the angular momentum of an electron in a state described with orbital quantum number L is equal to square root of L times L minus 1 multiplied by Planck's constant. So again, with no proof, and actually, I'm giving you a description from quantum mechanical point of view, but we're unable at this point to prove any of those formulas. Okay, so this is the orbital quantum number is the second of the 4 numbers needed to describe the state of an electron in an atom. The next quantum number that is needed is called magnetic quantum number, M. So an electron with magnetic quantum number N, the value of that magnetic quantum number ranges between negative L plus 1 through 0 all the way to L. In other words, the magnetic quantum number of an electron can be any of the 2L plus 1 possible numbers. In other words, if the orbital quantum number of an electron, let's say, is 2, the magnetic quantum number could be -2, -1, 0, 1, or 2. And finally, the fourth quantum number needed to describe the state of an electron in an atom is called spin quantum number, MS. And it has either a value plus 1/2 or value minus 1/2 in units of h bar. And that's pretty much it. Well, the magnetic quantum number also is in units of h bar, but let's leave it like this. So why do we bother to deal with this qualitative description of an electron? Because the entire chemistry of elements practically is an application of those results, of those quantum mechanical results. So if you know the quantum state of an atom, the chemical properties of that element follow directly from those four numbers. Okay. Yes.
Sorry, what was the difference between the L lowercase and the uppercase L?
So uppercase L is angular momentum. Angular momentum. So if you recall from the first semester, we defined angular momentum in classical physics as a product. So angular momentum of an object that is moving, let's say, this way, with linear momentum P equal to mv. So this is the linear momentum. This vector of represents the linear momentum. The angular momentum with respect to axis of rotation, let's say here, we defined as a product. Well, we defined it not as a vector, but as a scalar. But we defined it as a product of, well, the lever arm of this, or this, probably this distance is probably the better description. So if the object is located here, this is the lever arm L, and we defined the the angular momentum for this classical object with mass m as a product of the lever arm times the linear momentum of that. Well, that's good enough for us. This was from the first semester. In quantum mechanics, the texts look similar but different. In reality, actually, quantum mechanics can be considered as a simpler than classical mechanics. But again, we're not equipped, and it is not part of this course to discuss angular momentum. And I'm sure that, I'm sure that people have multiple questions because this mostly sounds like a story, and you can choose to believe it or not to believe it because I cannot provide any proofs. But just think about that. This is some part of modern physics that you can study, you can learn, and you can actually use it in practical applications if you're lucky. Dane, are you checking Google for orbital quantum number or for something else?
It's definitely something else.
That's a very honest answer. That's respectable. Okay.
But I could look that up for you if you want me to.
Well, feel free, but you have to describe the results for the rest of the class.
I'll bring out more next class. 3 pages. Tristan wants something to present. Yeah.
Tristan, go ahead.
Extra credit for both of us. Extra brownie points.
But you guys, you don't need extra points, right? Well, actually, most of the people in this section, don't need extra points actually, because you guys did very well. So well that I am forced to write a special version of the final exam, so you're not to be offended.
Because we did our work for the semester already.
Yeah. No, I don't have the right to free people from final exam. There's going to be a lot of commotion if I do that.
Well, you could just maybe give us a 1 point and one question exam that says like, which is the best physics teacher? We can just write your name.
But what if That sounds like a good physics final exam problem. Who is the best teacher?
You could even add that at the bottom, just as extra credit.
Yeah.
Well,
Be okay with that.
you're going to have the opportunity to get even for this for my teaching on Wednesday, because on Wednesday they are scheduled to come here and ask you end of semester evaluation, so you can get even finally. Don't use four-letter words because. Okay, so atoms, the four quantum numbers describing an atom. The next part of chapter 30 is a short description of two widely used devices. The first one is X-ray tube. Right? So most of the people here are in one or another biomedical major, and X-rays are widely used for medical imaging. How do you produce X-rays? Well, very simple, actually. You have isolated cylindrical volume with no air in it, and you have two electrodes in this connected to high voltage. Like, let's say, well, let's put this electrode much particular. So what do you do in order to produce X-rays is something quite simple. You apply high voltage between the two electrodes, and the result is something quite simple and easy actually to understand. First, the two electrodes here and here are made of metals, and metals, practically all metals, easily emit electrons from their surface. Especially if you warm them up a little bit, you have a cloud of electrons that are emitted around this piece of metal. So here on the negative terminal, on the cathode, you have usually a heated cathode, and you have electrons that are emitted freely. Under influence of the applied voltage, those electrons accelerate in this direction, and eventually they hit the anode. They hit the positive electrode, also made of some metal, usually some metal that has high melting point, like tungsten or something of that nature. The result of the collision between the accelerated electrons and this piece of metal is X-rays. You have a lot of heat usually also, but X-rays are emitted if the voltage between the terminals is selected appropriately. Usually of the order, well, you need a voltage of the order of thousands of volts voltage to have X-ray emission here. So using your knowledge about electricity and magnetism, can you have an explanation why the collision of electrons with metal atoms results in emission of X-rays? Well, the explanation actually is a little bit tricky if you want to figure it out in detail. However, the concept is very simple. Using the four Maxwell equations that you encountered this semester, you can demonstrate that any charged object that is subject to acceleration is going to emit electromagnetic waves. So acceleration, deceleration, the same story. And this is exactly what happens with the electrons when they hit the anode. They have acquired some certain velocity, they're moving fast, and suddenly they collide and they decelerate. The result of this deceleration, according to classical electrodynamics, is emission of electromagnetic waves. And if you have selected the voltage appropriately, those electromagnetic waves are going to be in the X-ray part of the spectrum. Actually, the spectrum of the electromagnetic waves emitted from an X-ray tube is a little bit, well, it has some structure. Well, if on the horizontal axis you have the wavelength of the emitted electromagnetic waves, and if on the vertical axis you have intensity of the electromagnetic wave lengths, electromagnetic waves with particular length, the spectrum looks like, well, it is kind of a smooth, continuous spectrum, maybe something of this nature. So no features expected if you do the calculations from the point of view of classical electrodynamics. However, in this continuous spectrum, you observe at least one, and more often more than one, bumps. So even though the continuous part of the spectrum can be explained pretty easily from classical electrodynamic point of view, the equations that we studied this semester, the presence of those bumps, those specks here, is a purely result of quantum mechanics, namely quantum mechanical properties of atoms. So think about the atoms on the metal with which the electrons collide, the atoms in the that are making the anode in this X-ray tube. So for those atoms, the collision with electrons is an accident, serious accident, and in the process of collisions, many of or some of those atoms in the anode are going, the electron is going to jump from normal ground state, let's say from state like this, into excited state with higher energy. So electron is going to go from here to some higher energy level. But excited energy states are unstable. They spontaneously, the electrons spontaneously move back to the ground state or to less excited state. And in the process, they emit photons with energy equal to energy difference between the excited and the ground state, exactly with that energy. The result is going to be a bump exactly at the energy corresponding to this transition of electrons from excited to ground state. So usually there are traditional names for those bumps in the spectrum, K alpha, K beta, but it is just a matter of notations. Something, well, it is a long descriptive chapter with multiple pieces from here and there, and the authors of the textbook felt compelled to give you something to calculate, which I'm not going to do, at least not in the final exam. But here, a feature of this X-ray spectrum is that there is a cutoff frequency, cutoff wavelength, smallest possible wavelength that this X-ray tube provides, lambda minimum. So remember that longer wavelengths correspond to photons with lower energy, and shorter wavelengths is higher energy of the photons in this part of the spectrum. So you can demonstrate, you can actually calculate exactly what is the cutoff wavelength if the voltage applied in this X-ray tube has value V, if the voltage difference between the anode and the cathode is V volts. And from the point of view of just understanding why do you have cutoff frequency, the understanding is very simple. The electrons that are accelerated eventually reach the anode with certain kinetic energy. If all of that kinetic energy is converted into the energy of emitted photon, so this is the maximum amount of energy that you can emit, that photon is going to have frequency corresponding to wavelength lambda minimum. And we can do the arithmetic here. So the energy of an electron that starts from the cathode and ends at the anode, that energy, we have calculated it, energy of the electron. We have proven that that energy is equal to the voltage between those 2 points multiplied by the charge of the electron, which is 1 elementary charge of the electron in magnitude. So this is the total kinetic energy of an electron that reaches the anode. If all of that energy is converted into energy of one photon, well, the energy of a photon, let's say energy of the photon gamma, is given as, well, the formula in a standard way for a photon, energy of a photon looks like this. Linear momentum of the photon in magnitude is equal to the energy of that photon divided by the speed of light. In other words, the energy of the photon, E, is equal to the product of linear momentum of the photon multiplied by the speed of light. But, okay, now I want, instead of using linear momentum of a photon, I want to switch to wavelength. And you do this by using de Broglie's formula, which says that linear momentum is Planck's constant divided by wavelength. So substitute it here, and for the energy of the photon, you get h, Planck's constant, speed of light divided by the wavelength corresponding to this photon. And now, remember, this is energy of, kinetic energy of accelerated electron. This is the energy of the emitted photon. If all of that kinetic energy is converted into energy of a photon, you have E of the electron must be equal to the energy of the photon. In other words, you must have You must have voltage difference between anode and cathode multiplied by the elementary electric charge has to be equal to Planck's constant multiplied by the speed of light and divided by the wavelength. And this is going to be your minimum wavelength, cutoff wavelength for this X-ray tube. And from here you say the cutoff wavelength is equal to Hc divided by voltage and divided by elementary electric charge. You don't need to be able to derive this formula, but you have to know that what this formula actually represents in case if you want to do correctly the multiple choice questions, let's say, on the final exam, or if you want to finish the homework assignment on chapter 30. Well, so this is probably the only derivation that you have in this chapter. And again, you don't need to be able to reproduce it. But the idea about this cutoff frequency is interesting and important because in order to derive this formula, you have results from classical electrodynamics. Namely, this formula is a formula that we have derived, we have used this semester. This formula is a result of special relativity. So, in a sense, knowing this cutoff frequency, being able to theoretically calculate it is a check of classical electrodynamics and fundamental results from relativity. Okay, any remarks and issues here? X-ray tube? What do you think about X-ray tubes? Useful? Okay. The last section of this chapter is describing how lasers work. And the idea there is very simple, even though the practical implementation of those ideas is not that trivial. So a laser consists of active material. Let's say here is, let's say active material could be some solid crystal, it could be gas. So let's say that this active material in this cylinder is some gas, let's say neon or some other gas. What you do is, again, usually you apply high voltage and bring a fraction of the atoms of this gas into excited state. So in other words, you have electrons in this active material that are brought into some excited state. And you already know that excited states are unstable and the electrons spontaneously eventually are going to go back into lower energy states. And again, in the process of this transition, the electron is going to emit a photon exactly with energy equal to the energy difference between the excited and lower energy level. Exactly that energy. So, well, this is good, but there is one more detail that makes lasers possible. Using quantum mechanical reasoning, you can demonstrate that if you have let's say, two energy levels, and the electron is in the excited state right here. And if you have a photon coming in here exactly with the right energy, exactly with the right wavelength, corresponding to the energy difference between the two states, that photon is going to generate spontaneous transition of the excited electron into a lower energy state. So look, the electron would fall to lower energy state spontaneously by itself. But if there is another photon with the right energy, the transition is going to be stimulated. It is going to happen with higher probability. So if this photon with the right energy comes in and transition occurs, that photon that came in is going to continue, but you're going to have a second photon, a result of the transition of this electron to lower energy state. In other words, you started with a single photon with the right wavelength, with the right energy, and you ended up with two of them. Each of those two photons eventually may encounter another excited atom and may generate another stimulated transition, and therefore each of those two photons is going to multiply again. So from one, you have two, after that you may have four, and so on. The result of this sequence of simulated transitions is an avalanche of photons, exact carbon copy of each other, exactly the same energy, exactly in sync. In other words, they generate, they make up a coherent transition, a coherent beam of light with exactly the wavelength equal to the energy level difference between excited and lower excited state. So this is what you do in this active material. And well, in order to produce more photons with this exact wavelength and coherent electromagnetic wave, you put two mirrors, one of them with reflectivity 100%, the other one semi-reflective mirror. And look what happens. So one excited atom in the active material spontaneously drops and generates a photon. And that photon acts with other excited atoms and generates an avalanche of photons of the same wavelength. And the result is a light ray in arbitrary direction. However, once this light ray hits the mirror, most of it is going to get reflected, come back, and in the process produce more and more photons, simulated emission. And you're going to have multiple back and forth paths of this simulated emission light. And eventually from the semi-transparent part of the mirror, you're going to see the laser beam getting out. So this is roughly how lasers operate. Now, depending upon the nature of the active material, is it going to be gas, or is it going to be some crystal, or maybe some semiconducting material, you can produce laser light within wide range of wavelengths. And that laser light is going to be monochromatic and coherent. And with a little bit of more detailed analysis, you can demonstrate that actually you can even produce, you can make lasers that have variable wavelength of emission of electromagnetic waves of light. But for the moment, this is the principle of operating of a laser. Okay. Any remarks? Any questions so far? So again, from this chapter, you practically cannot do any quantitative type of question, but the concepts is what you have to understand in order to feel comfortable.
What would be like an example of a concept question you could ask about laser beams?
About laser beams, yeah. Let me show some. Okay, so let me start here. I have conceptual questions, but the homework assignment probably is the best source of the type of questions that you are going to encounter in the final exam. Again, we don't have the time to have a practice test and have it solved and analyze it. And again, the material here is mostly qualitative. And but let's look at the following conceptual questions that are, in a sense, similar to conceptual questions that you're going to encounter in chapter 30 homework and chapter 31 homework assignments. So if you look at the following question here, let's see. And the first question is quite actually, you guys, you should have asked about this when we talked about Rutherford scattering experiment in his planetary model. Because this planetary model has one big, well, it has multiple shortcomings, but this one is a big one. So before you choose your answer, so basically this problem is asking you this. You have a nucleus, atomic nucleus, with multiple protons in it. Protons carry positive electric charge, and therefore they repel. And since the distance between the protons in the nucleus is very small, the repulsive force, according to Coulomb's law, is very strong. The question is, why doesn't a nucleus break apart? Because of the Coulomb forces. And, well, keep in mind that none of the above is perfectly good choice. Right, this is. Now, before I go to the next conceptual question in this presentation, let me ask you something about practical applications of this model, quantum mechanical model of atoms. So this simple picture of electrons in an atom that are only allowed to occupy energy level corresponding to principal number, quantum number 1 or 2 or 3 or 4 or so on. That model is the base for the entire atomic spectroscopy with wide application, practical applications. Because look, if under certain conditions you create certain number of atoms in which the electrons are in excited state, those electrons eventually are going to fall back to lower energy states. And in the process, they're going to emit their energy as a photon. That photon is going to be monochromatic, always the same energy, therefore the same wavelength. And therefore, in excited set of atoms, you're going to see a single emission spectral line specific for this particular type of atoms. So what you do is you take a sample in order to do spectroscopy. You take a sample of your material. You create excited states usually by heating up this material or passing electric current through it so that you generate excited state atoms. And after that, you observe as those atoms, you observe the light that is emitted. And you should see a specific color, a specific spectral line. So for example, here, what is mounted right here is, right now it is a neon tube. So neon is a gas, and you pass an electric current pretty much like in the fluorescent lights here. Well, if you look with a diffraction grating at the emitted light, you should see clear emission spectral lines specific for the neon gas. So what you have to look a little bit aside, but what I see here are one bright yellow and several red, orange spectral lines. So the colors of those monochromatic spectral lines are specific for neon. If I change the material, if I put, let's say, instead of a neon, if I put, yeah, you have to do it because I'm afraid I not break this thing. Well, if you break it, it's going to be fine. But so now, what is this gas? Is nitrogen. You're going to see different spectral lines for nitrogen. Again, specific for nitrogen. So when I look at this, this diffraction grating doesn't show me much, but probably yours may show you some spectral lines. Well, I don't see any. Can you change again to something different? Okay, now it is what? Helium. Okay, spectral lines of helium. Helium is the second most common element in the universe. And you see a very nice blue, actually a couple of blue lines, a green line, and an orange one. Well, you have to look at it like this. So those are the basics of spectroscopy, atomic spectroscopy. And this is how we know what elements, distant galaxies and distant stars are made of, just from the spectral picture of those elements. The spectral lines that you observe here are called emission spectral lines. In addition to emission spectral lines, especially in astronomy, you also observe absorption lines. Absorption lines are dark parts of the place where emission spectral lines are. Instead of bright light, you see dark spot, dark lack of atoms, lack of photons with this particular wavelength. So the mechanism for generation of absorption lights absorption spectral lines is slightly different, and we're going to talk about it on Wednesday. On Wednesday, we're going to start also chapter 31, radioactivity and yes.
Is the final very heavily centered on these new chapters and chapter optics that we covered last?
So the final is going to have questions from the new material. This is chapter 27, and chapter 27 is interference diffraction of light. Over there you have formulas, and you have to be able to calculate, let's say, some geometry related with interference pattern. Let's say you're given distance between two bright spots in interference pattern from diffraction grating or from two-slit experiment. You're asked what is the wavelength, or using that geometry figure out something about this diffraction grating or about the light that you use. You're also going to have from chapter 27 resolving power of human eye optical instruments. So those are pretty much the few calculational questions that you have from this material. From the new chapters, you have a good sample of questions that you're going to have from the new chapters, from chapter 30 and chapter 31 in the homework assignment. So the homework assignment, if you understand the question in the homework assignment, you're going to have some variation of that concept in the final exam. And you're going to have multiple choice questions from all over the semester. Questions, conceptual questions that you have already encountered, either in a practice test or homework assignment or just in class. And you may have, let's say, one or two calculational problems from the old material, and I will tell you exactly what type of calculational problems you have to prepare from the old material. Again, all conceptual questions are fair game. But calculational questions from the old material, I'll give you some direction. So you don't need to be overwhelmed with all the material that we studied over this.
Last semester, the final was like 3 long answer questions and then like 15 multiple choice about the line.
So exactly how many questions are going to be on the final, I don't know before I write it. So, but roughly the same number. So is it going to be 15 conceptual and 3 calculational, or it is going to be 20 and 4, or it's, but you're definitely going to have sufficient time to finish it, yes.
Are we going to get a practice test kind of thing for the final?
No practice test. So for the old material, you use the old practice test and homework assignments. For the new material, you use the homework assignments. We don't have time for practice tests. This is the end of the semester. Okay. Any other remarks, questions? So don't feel stressed about this final exam. Think about it as something that is fun. And absolutely, yes. Okay. So see you on Wednesday.